Jacques is currently a Marie Curie Research Fellow at MIT, where he's working in the photonics laboratory. And Jacques is going to talk today about large-scale silicon-based quantum photonic processes. Okay.
Can you guys hear me? Yes, you can. Perfect. Awesome. So, yeah, my name is Jacques Carolan. It's great to be back in Bristol, not least for the weather, but also to see that I think there's something very quintessentially Bristol about having reusable cups and fair trade coffee. So, yeah, it's great to be back. I'm going to be presenting a kind of very general picture of a quantum photonic process, and following on from Mark, really zooming in on this kind of universal types of linear optical processes that we can do. Okay? And there's a number of reasons why you might want to do this. First, it presents a significant resource saving in terms of, say, graduate hours. Okay? It allows you to test your known protocols in experimentally realistic scenarios, and perhaps most excitingly, allows you to develop new protocols. Okay, so I'm going to talk about two pieces of work. One, which is in the platform of silica, okay, which we worked on back in Bristol. Okay, and I'm going to talk about our efforts to scale this up in silicon at MIT. Okay, and what you'll see is that every time you kind of change this platform, you will get some new functionality to that, whether that's in quantum computing, quantum simulation, or, I know it's rather a dirty word in these parts, classical applications. Okay, now when you start building large-scale chips, there will be classical applications of this. I'm going to talk about some applications in optical neural networks. Okay, so why are we interested in photons? Well, you know, they have all of these wonderful properties: fast propagation, ease of manipulation, low noise, and because of this, I make the argument that they're going to be involved in virtually all quantum technologies, okay? Whether it's to mediate interaction between some kind of matter-based qubits, okay, whether it's ions or NV sensors or superconducting qubits, okay, or as a qubit themselves, whether you're going to store information on some kind of discrete degree of freedom or perhaps some kind of continuous degree of freedom. And the point is that when you advance integrated photonics, you advance both of these applications. Okay? So integrated photonics, you know, allows us to guide light in a single mode on chip, and we've got a whole host of kind of material platforms that we can look at to do this, whether that's silicon on insulator, you know, more glass-based circuits, or even silicon nitride. Okay? You can choose whichever one you want. We get passive control by manipulating, for example, the evanescent field of the waveguide and coupling to neighboring waveguides to be directional couplers, or actually physically changing the geometry of the waveguide to do things like on-chip filtering, or do things like, you know, enhance the interaction of the light with some material of interest. Okay? And finally, we can have active control over these systems through actively modulating the effective refractive index of the material, whether that's through the thermal optic effect, whether that's through some kind of MEM-based devices which can pick up around kind of megahertz modulation speeds, or even carrier effects as well, where you can hit gigahertz. Okay. All of these kind of tools are available to you in the kind of quantum photonics toolbox. So that means we have a platform which is potentially stable. Okay, it's on chip, it's intrinsically stable, it's compact, we can get devices, and these are devices which I'm going to be talking about, which have hundreds of components and just a few millimeters squared, and it points the way towards scalability. And why I'm kind of reticent to say it's truly scalable is that, you know, just because you can come up, just because in silicon, doesn't mean you can come up with some crazy design and throw it in Intel's process, because they won't touch it. But the recent work towards these zero-change architectures, which we heard about, seem very promising, okay? Where you get your memory bank and your processor to speak via light. And that's actually using the crystalline transistor layer of the CMOS process to guide light. Okay? So for me, that's super exciting. So, because of all this, we've seen, you know, a bunch of amazing demonstrations, proof of principle demonstrations of Shor's factoring algorithm, first demonstrations of you know, quantum simulation with evanescently coupled waveguides. You can increase the control over these types of systems, okay? Whether that's you know, reconfigurable 2-qubit entangling gates, You can do tomography, draw size in the block sphere. You can find the ground state of helium hydride, and even this beautiful work from the guys in Bristol, scaling it up to have high dimensional entangled states. And you can even increase the complexity, put more photons in this system, and verify quantum interference in some large Hilbert space. But the point I want to make here is that each of these experiments require distinct linear optical circuits that take often years to design, fabricate, and test. Now, if you can configure your circuitry in a very particular way, it turns out you can do all these experiments on a single chip. Okay? And we say the system is universal for linear optics. So to kind of understand this point, let us first know what are toolboxes of linear optics. Okay? So we have things like beam splitters and phase shifters, where in the lossless case, these are described by unitary matrices, okay, where each element of the matrix gives some probability amplitude to transition from a given input mode to a given output mode. Okay? And it's clear that if you kind of plug these things together, simple matrix multiplication will tell you that a large linear optical circuit is also described by a unitary matrix. Now, back in 1994, Rechenzeilinger showed that if you have a particular configuration of beam splitters and phase shifters, this triangular configuration here, you can implement any unitary operator on modes, and therefore any linear optical circuit. Okay. And there have been some different advances along these lines towards different architectures which are also universal and perform better under certain metrics. Okay. And I like this paper for a number of reasons. It's a very beautiful proof. I also like it because it's got the word experimental realization in the title, and there's no experimental realization. and the story goes that Michael Reck actually spent his PhD really trying to build this, but it was just too hard in the kind of bulk optical systems or fiber optical systems they were looking at. Okay? So it turns out he couldn't do it, and from what I understand, he became a consultant at IBM. So I kind of feel like this is cursed somehow. Right? So against our better judgment, the team in Bristol, we attempted to try and build this. Okay? So this was a collaboration with NTT in Japan, where we made a 6-mode universal system in silica using planar lightwave circuit technology. So the system consists of 15 mach-length interferometers and 30 thermo-optic phase shifters. So if we zoom in on it, we see you have this germanium-doped silica core surrounded by a silica cladding. So it's got a very low refractive index contrast. And it means you have about a 10mm bend radius. So the device, as we've already heard, is very large. Okay. But for our purposes, it's really like having fiber optics on chip, which means you get very good coupling on the input and output. And that's important for these kind of multi-photon experiments, which we wanted to do. Okay. And because of this, we can do a whole host of experiments. Whether that's in the computational model, looking at heralded quantum logic gates, where you use 2 ancilla photons and 2 computational photons, and detection in the ancilla mode tells you that you perform the computation on your computational photons. That's in the circuit model. We can also look at things in the cluster state model, where we can herald the generation of entangled states, Bell states, this Bell state generator. And we can also do things like full quantum process tomography on this system as well. And we're not only limited to the kind of computational model, we can look at non-computational models as well. Okay? So we can look at many instances of boson sampling, we can come up with new types of verification procedures, and we can finally, because the loss is so low, we even saw some 6-photon events. So we could come up with a discriminator that gave us confidence we were sampling from a quantum distribution as opposed to a classical distribution. So this is all well and nice, and we've heard how we can go from something which is, say, meters in scale to something in centimeters in scale, but how do we go for something that's smaller than that? Because we really are at the limit of what you can almost do in a single wafer. Okay? And as we've heard, we need something with a much higher component density. And the answer to that seems to be silicon. Okay? And in part, due to this significant investment in the microelectronics industry for photonic interconnects, there's been a huge amount of money towards the Silicon Photonics project. Okay? So you get a very high refractive index contrast, which allows you to have bend radius down on the kind of micron scale. Okay? So this is one of a beautiful paper from Mike Watts' group, where they make these phased arrays, and they get 4,000 optical components in just a few hundred microns squared. So this really tells you the scale of the devices that you can have. This thing can be relatively low loss, okay? You can even get better than 3 per centimeter, but the key metric is kind of loss per component. And in that case, it does incredibly well. We also can potentially start integrating electronics into the system through the CMOS platform, and perhaps most importantly, most exciting, we get a strong Chi3 nonlinearity, so we can generate new states of light. So you can go to your foundry and you get a whole host of kind of tools in which you can try and use in this quantum regime. So towards this end, we've tried to scale up this universal processor in MIT through the silicon photonics pattern. And this is the device that we developed. So it's over 26 optical modes on the input and output, and it has 88 max-end interferometers and 176 low-loss thermoptic phase shifters. And if you kind of zoom in, we see we're really just a few hundred microns for a max-end there. Okay? So it's a really significant scale difference. These thermoptic phase shifters are incredibly low loss. Okay? When we put them inside a ring, they actually don't even degrade the quality factor of the ring. It's very hard to measure the loss of these. And because they're so low loss and because they're so efficient and so small, we can get down with just a single max-end interferometers to a 66 dB extinction ratio. Okay? So it's a really impressive technology. So if we try and build something like this, what type of fun things can we do? So the first thing I want to show you, this is what our characterization process is. So we put telecom laser light in and we image over the top with an infrared camera. Okay? And this is what you can see. So this is actually real time, and this is our calibration procedure for the device. So the fact that you're seeing something means that there's loss, and of course there's loss, but these cameras are also very sensitive. But for me, it just kind of gives you a scale of the kind of complexity of this type of system. Okay. So if we have one of these type of devices, what type of cool things can we do? Okay. So, well, actually, the first thing we need to know is that even just controlling this device is a serious systems engineering challenge. Okay? There's 240 pads on this thing, so you need to somehow wire bond 240 pads. Optically, we're using a very non-standard waveguide pitch as well. So we've got 25.4 micron mode spacing. So we've had to actually design separate photonic integrated circuits, laser-written glass PICs, to in-out couple of this device. And not only does that get us down to the correct pitch, but it also does some mode transformation as well, so we can reduce the loss on this device. The electrical component is significant as well. If you just look at the kind of GDS for this device, it's hugely complex. And trying to lay something like that out is highly non-trivial. Okay? So there's a huge amount of complexity in this. We've had to develop custom-built electronics to speak to this thing, 240 channels, 16-bit precisions. Also, to do this calibration procedure that I was talking about, you need to find an array of photodiodes. We've had to build a photodiode array where each photodiode gives us 50 dB of dynamic range. Okay? So a significant amount of electronic engineering has to go into this. So given that you can kind of build this type of system, what can you do with it? So it turns out that this type of system is well suited to looking at quantum transport effects. And to understand quantum transport effects, let's first consider a highly ordered crystal, okay, and an electron in a highly ordered crystal. Now, we know from solid-state physics that the wave function is described by a block wave which is delocalized across the entire crystal. Okay. Now, if you add some static disorder to this, what Anderson showed back in the 50s was that you get this localization effect, okay, which is due to the interference from scattered wavelets of these different sites. Okay. So this is purely an interference, single particle interference effect. Okay. However, if you add some dynamic disorder to this system, okay, where you move each of these lattice sites, you effectively unstick, you kind of dephase this coherent interference effect. And you unstick and you see some, the electron on average moves further away. So this thing is known as environment-assisted quantum transport. Okay. And then this is interesting for a number of reasons, partly because people have started to look at this kind of feature in biological systems for trying to explain why certain photosynthetic complexes have very efficient transfer. Okay, now, this is still up for debate in a lot of the literature, but this perhaps motivates even more why you might want to look at this experimentally. And I'm just going to do a very quick shameless plug at this point, where I'm actually helping organise an analog quantum simulation workshop in Bristol in the middle of July. Okay, so this is half in the philosophy department, half in the physics department, but if people are interested in quantum simulation, there's going to be some awesome speakers in optical atoms that are going to be there, so totally come along, and maybe someone from Bristol as well speaking. So anyway, that was that little detour. So how do we realize that in our system? Okay, so what I want to say is that this is a schematic of our device. We're going to put classical laser light in. The time axis is going on the x, and spatially is going to be y. Okay? And what we're going to do is set the internal phase shift of each of these guys to pi on 2. So you possess an equal probability to go and split right or left. And we're going to put a phase shift on the output. And the phase shift is going to tell us what the type of disorder we've got. Okay? So what we want to do is increase this dynamic disorder and see what the probability to transition from a given input mode to a given output mode is. Okay? And what you can see is that to begin with, when you have very low dynamic disorder, you get a low efficiency of transfer. So this is the efficiency of transfer, this is disorder. Okay? So this is the Anderson localization regime. Okay? As you increase it, we get this unsticking that I spoke about. Okay? This is a kind of, effectively they call it the quantum Goldilocks regime. But as you increase the dephasing even more, you end up in a kind of quantum Zeno effect, and you reduce your transfer efficiency. Okay? So what can we say about this? Well, I want to be completely clear, this is a single particle effect. This is classically simulable. But I think it's an interesting question is what happens when you start putting multi-photons into this system? Okay, and that's a kind of open question. What happens to these transport effects? So along those lines, we've also been looking at how we can start getting single photons onto this system as well. Okay? Using the intrinsic nonlinearity of silicon, the chi-3 nonlinearity. So Mark's already given a wonderful introduction to this. But for our process, we're using these micro ring resonators to essentially give us these well-defined resonances such that we pump at these two neighboring resonances will produce photons in the central one. Okay? The details of this device aren't so important, but what I want to say is that one of the hardest things of actually using a device like this is that you've got a number of high Q rings. Okay? Each ring has about 40 or 50,000 quality factor in a few hundred microns squared, and they're all thermally controlled. Okay? So what you find is that this thing crosstalks with one another. Okay? And moreover, because there are rings inside the interferometer, you have very high phase sensitivity. Okay? So just to kind of see this, we artificially induced a temperature change on this device, okay, over the course of an hour of 1 degree centigrade. And if you guys are involved in kind of emitter spectroscopy, this really is just looking at the resonances of the rings. And as you can see, if we change it by a degree, we change by almost 3.5 times the line width of the system. Okay? So this is just a single degree change. So what we've had to do is develop new optimal control techniques to actually correct for this in situ. And what the nice thing about photonics is that you can do a huge amount of your characterization and correction using classical laser fields, okay, where you have a very high signal-to-noise ratio. Okay? So using this in situ optimization technique, we can make this thing completely flat, okay? And we see that we have, this isn't so clear, but we get down to 10 to the minus 3 variation in the line width of the ring, so very high accuracy. And the point is, even if we take our best model of how this system changes with temperature, we only get down to basically, 10 to the minus 8 times 10 to the minus 2, okay, in terms of line width variation. So it really seems that the best way to get ultra high stability of these systems is to develop some kind of new classical optimal control techniques. And using this, we can demonstrate very high classical extinction ratios, we can see high quantum interference, 97%, and we can also see a very bright photon source. This is just what we see on the output. This isn't accounting for facet loss, tens of kilohertz, and very high coincidence accidental ratio. Okay. So the final thing I want to talk about is classical applications of this device. So if you only want to hear about quantum, you can turn your ears off now. there's been a recent explosion in years in deep learning. Okay? Deep learning is a computational model inspired by the brain, okay, which has done exceptional has achieved exceptional fidelities for image and speech recognition, language translation, and decision making. Okay? And trying to understand this computational model, okay, is actually relatively straightforward. What you do is your input data is encoded in this vector of real numbers. Okay? So maybe it's a grayscale image. Okay? So you have this input data, you pass it through a matrix operation, which is parameterized by some weights. See that here? And then you pass it through a nonlinear activation function. Okay? And the aim of the game is to train these weights to realize a particular input-output configuration for some large set of vectors. Okay? So let's take the prototypical supervised learning example. Cats. Okay? You want to figure out if an image of a cat is a cat. It's a very important thing you need to do. So what you're going to do is you're going to take a whole set of images of cats. Okay? They're going to be grayscaled. Okay? So you can encode them as some vector. And then you're going to train these weights to always output the vector cat, maybe 1, 0, 0, 0, for example. And you do this over some large training set, such that when you give it a new image of a cat, it says, hey, you've got a cat. Okay? Now, why might this be good in photonics? Okay? Well, at the core of this, you're doing matrix multiplication. And as I've already said, optics is very good at doing matrix multiplication. Right? So, what that means is we could potentially get incredibly high bandwidth. Okay? You can get germanium photodetectors at 100 gigahertz speed already at the moment. And I just want to be completely clear, this is purely classical what I'm describing. And potentially you can have very low power consumption as well if you can make your circuit very low powered. So what would this kind of optical neural network look like? So your input vector is going to be encoded in some laser light. You're going to pass it through some circuit. Now this can be active using these thermal-optic phase shifters, or it can be purely passive using some kind of set and forget technology. Maybe you want to use phase change materials, maybe you just want to fabricate very accurately, whatever. And then you want to go through some optical nonlinearity. What ways can you do this? Well, you could use the intrinsic bicestability of silicon, for example, or maybe you could integrate something a bit more crazy, graphene, a Sacher absorber like carbon nanotube, something like that. And you're just going to repeat this guy. So for this proof of principle demonstration, we categorized Chinese vowels. Okay? This was a 4-layer, 4-neuron problem, which we simulated for this proof of principle demonstration in just a single layer. Okay? And the nonlinearity was applied in software. Okay? And then we then repeated this. And what you see is we got 72% correct identification versus 92% on a digital computer. And this is in part due to the kind of finite precision of our phase shifters, okay, which can be made better. So this is kind of most of what I wanted to talk about. I've shown how you can build these universal devices, and there's a whole host of things you can do with them, right? Whether that's in the kind of quantum computation regime, we've talked about how we can like scale this up, single photon sources, and even doing some kind of classical processing on top of that as well. The final thing I want to mention, just to kind of end on, is my dream for silicon photonics. Okay. Now this is what my dream is. Okay. And you know we're in Bristol, so I think we should talk about upcycling things. Okay. So my dream is to have sources, circuitry, and detectors integrated within the silicon platform. Okay. And my claim is that silicon photonics offers you unparalleled complexity and scale. But what you might want to do is start integrating more exotic things into this system. Okay? For example, perhaps we can integrate quantum dots into this system. There's this awesome work from Ido Wax's group, which is to integrate these indium arsenide, indium phosphide quantum dots, which emit at 1300 nanometers. Okay? So you could do this kind of pick and place technique, or maybe even stamp them on there. Okay? So that's like how you might want to get a really good source. In terms of the actual circuitry, well, I've shown how we can do high fidelity thermal phase shifters. Maybe you want something that's more cryogenically friendly, okay? You can use these either phase or shape change materials. Chalcogenide-based materials have started to become incredibly low loss. Maybe you want some kind of classical nonlinearity in this system through the introduction of graphene or carbon nanotubes, or maybe even want some quantum nonlinearity. As we'll hopefully hear over the next few days, quantum dots have a very high nonlinear activation. Okay? So perhaps we could integrate that within the system as well. And maybe you want to do some kind of, as Mark spoke about briefly, you can actually induce Chi2 nonlinearities in the system by breaking the symmetry of the crystalline. So this is potentially exciting because it means you can get an electro-optic effect in the silicon. Okay. And finally, how can we get detectors on there? Well, we can perhaps pick and place them on there, or well, you can get pretty low loss coupling, of the order of 0.1 dB using grating couplers, using more exotic technologies, but it seems to be possible. So this is my dream, to kind of integrate all of these more exotic technologies within the Silicon Photonics platform. And we've got efforts in virtually all of these in MIT, and I'll be happy to speak about that further. So thank you all for listening.
Thank you, Jacques. Any questions? I have one. Why Chinese vowels?
It's a kind of prototypical machine learning example, and it's one you only need 4 neurons for as well.
Okay.
So the sound was actually broken up into 4 logarithmically spaced kind of frequency bands, and you can use that to train it. Yeah. So you need to find something which is suited to the size of your system. And if you try and think about building this thing large scale, you're really not going to be able to compete with the millions of neurons that Facebook use. So what you really want to do is find very specific examples which you can do perhaps more small scale. Yeah.
Thank you. Any other questions?
Did you need to reconfigure also the nonlinear response of the circuit, or only the linear part?
So the nonlinearity can stay fixed. So in our example, we use software for this nonlinearity, but the nonlinear activation function is the same all the time. What you do need to be able to change is the bias into that. It's very important that you can change the bias. So we're looking at how we can actually do this nonlinearity on chip, and then you need some way to fix the bias. But that's actually totally feasible in optics. Yeah.
Regarding the Fussell merger ratio between 2 ring resonator sources, do you have any full Fussell data?
No, this is a 2-photon experiment. This is a 2-photon experiment. Yeah.
And there was another question.
Could you please comment a little bit how the deep learning approach that you discussed compares to reservoir computing?
Say the last part again.
So
Reservoir.
you saw an approach which is not based on reservoir computing. So can you comment a little bit how this approach compares to that?
Yeah, so my understanding is that reservoir computing is well suited to doing time series data. Okay, where you have essentially you have your network and you have loops within the network. For our system, it was completely linear in time. I think they are both complementary, and I think it's an interesting question how you could perhaps integrate these kind of reservoir approaches, and I know that people already are, into the Silicon Photonics platform. Yeah.
Time for one more question.
One question about your quantum transport.
Yeah.
One question about your quantum transport experiment. In what way that's different than doing like a step, like a discrete quantum?
It's a discrete quantum walk. It just gives you some variability in how you control it. Yeah, it's a discrete quantum walk, for sure.
Okay. Jack, can you remind us of the date again?
The 17th and 18th of July. Speak to me if you're interested in analog quantum simulation.
Cool. Thank you.
Cool.
Thank you, Jack. Yeah.